Today we're going to start an introduction on probability, but to do that we have to start with combinatorics and the counting principle. And what the counting principle talks about is it says if there are A ways to do one activity and B ways to do another, then there are A times B ways for both to occur. So if I have an example like this where Joe needs a suit and a tie, and we know that the suit comes in black or blue and is made of silk or wool, and the tie is either stripe or solid, how many different selections can he make? Well, we know we have two possibilities for the color, and then we have fabric, also two possibilities, and then a tie that's either striped or solid. Two possibilities. So when I multiply those together, I have 8 different ways I can make that suit up. Another way to do this is to do a diagram where you have a blue suit or a black suit, and then off of that I could wear a blue suit and either a silk or a wool and a silk or a wool, and then from that blue silk suit I could either go solid or stripe, solid or stripe, solid or stripe, and then solid or stripe. And what this has done, this is kind of called a tree diagram. It gives us all the different possibilities. So for instance, this is a blue wool suit with a solid tie. And you can see at the end of this I have 1, 2, 3, 4, 5, 6, 7, 8 choices. If I go through and list all the different possibilities, it's called a sample space.
We've got a guy who fishes. He's got 5 poles, 4 types of line, and 43 different lures, and you want to know how many different fishing setups he can make. Well, again, one item of choice is the poles he can use, and he has 5 of those. He's got the line choices. He's got 4 of those, and he's got the lure choices, and he's got 43 of those. And I want to know how many different ways he can put together his fishing setup. I just multiply all those together, and that's going to get me 860 different setups. Now, if you toss a coin 5 times, you want to know how many different arrangements of heads and tails can be made. Well, again, we can do a tree diagram for this, and sometimes that's actually going to help. But all we really have to do is consider each toss a different set of choices. So on my first toss, I have 2 outcomes. On my second toss, I have another 2 outcomes. On my third toss, another 2 outcomes. Fourth toss, another 2 outcomes. And fifth toss, another 2 outcomes. So really what I have is 2 to the 5th different ways to do this, or 32 different combinations of heads and tails depending on the number of times I toss the coin. If I want to find out how many different 6-space license plates can be made with 3 letters in the first space and 3 numbers in the second 3 spaces, then what that says is I have 6 different events happening. The first event is for the first space, and I can only choose between letters. So I have 26 different letters to choose from in that first spot. This problem doesn't mention anything about not being able to repeat letters, so I have 26 choices for my second spot and my third spot. When we start talking about choosing numbers for my 3 spaces at the end, remember you can only use single digit numbers. So we've got the numbers 0 through 9, which is 10 possible numbers here. And since they could repeat, I have 10 here and 10 here. So this is, whoops, I can't believe I just put 23 right here instead of 26. But which gives me 26 to the third power times 10 to the third power, which is a pretty big number. About 17,576,000 different license plates. And you'll notice we've only got 6 letters here. California used to be a six number license plate, and they went through over 17 million combinations, which is why we now have, I believe, 7-digit license plates. We're not talking about vanity license plates, different. So we want to know how many ways we can arrange the letters in the word cat, and we can do this kind of in an intuitive way. We have 3 letters to place in 3 different spots, and in this case we could have 3 choices for our first spot, 2 choices for our second, 1 choice for our third, or a total of 6 different ways, and I've listed them all over here. Again, you can calculate that going P33. You'll get the same thing. Now we want to know how many ways can the letters in B be arranged, and you would think it's the same problem as cat because we've got 3 letters and 3 letters here. However, the B's repeat themselves, and we call these indistinguishable. So you can't tell the difference between one E and another E. And if that's the case, I've listed all the different possibilities here, and we only have 3 different arrangements. So what we've got is we've got a new type of equation where the number of different permutations of n objects, where n sub 1 are indistinguishable objects, n sub 2 could be indistinguishable, and so on and so forth. The total number of permutations is n factorial. We take the total numbers, factorial it, and then divide that by each number of items that's indistinguishable, and it's factorial. So in this case, I had 3 factorial, and E repeated itself twice, so I'm going to divide that by 2 factorial. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. Reduce out, get a total of 3 different arrangements, which is what we had. Let's do some more practice. Number of ways to arrange the letters in the word Erie. We've got a total of 5 items, so that's going to be 5 factorial. E is the only thing repeated, and it's repeated 3 times. So that's just 5 factorial over 3 factorial. You can work this out without a calculator. It's 5 factorial over 3 factorial. Those reduce out, we get a total of 20 different ways. So you got 25 Christmas lights, 10 are blue, 5 red, 4 green, and 6 yellow. How many different arrangements of those 25 lights can you have? Well, we're taking all 25 and arranging those. We've got a whole slew of repeats. 10 blues, 5 reds, 4 greens, 6 yellows. And this can all be done on a calculator. And the answer in this case is rather large. We get about 2.06 times 10 to the 12th power. Want to know how many ways letters in Shakespeare can be arranged? Let's start breaking down the repetitions. We have the S repeating, the E repeating, A repeating. I think that's it. So we've got a total of 10, 11, 12, 13, 14, I lied, 5, 6, 7, 8, 9, 10 words. Lied again, 11 words or 11 letters. And next we're going to arrange the letters in Shakespeare, counting for the repetitions. In Shakespeare is a total of 11 letters. That's 11 factorial. The S repeats twice. H does not repeat. A repeats twice. K does not repeat. E repeats 3 times. P does not repeat, and the R does not repeat. So this will get it done. You can grind that out on your calculator. So that was basically it for the new piece. Now we're going to do some mixed review. And in many cases, some of these are going to be a little more difficult. So in this problem, we have a banquet table where you've got 2 senators, 2 ambassadors, and 3 mayors. And we're going to find out how many ways they can be seated by title. So what I mean by title is that even though the 2 senators are different, because we're arranging them by title, a senator is a senator is a senator, so they're indistinguishable. So this is still a little bit of these linear permutations with repetition. So I have a total of 7 seats, but my senators repeat, my ambassadors repeat, and my mayors repeat. So this would be the first part. Now the second part, we want to know how many ways they can be seated by title if the senators must sit on 2 ends. So this problem is a little more difficult, and we're going to have to diagram this out actually. So if the senators are going to sit in 2 ends, that means I get either my senators here or I get my senators over here. In each case though, you'll notice that because my senators are here and I can flip-flop them, and since we're talking by title, neither arrangement is different in either of these cases, it really leaves me with only 5 ways to place the other people. So what I've got in both cases is I've got 5 factorial, and then I'm seating ambassadors and mayors. So I have repeats there of 2 factorial and 3 factorial. And that will be the same in both cases.